you have almost certainly written C++ code like this. It looks very simple. Create an array and then keep adding data to it. But the question is, when calling the pushback method, what does C++ actually do? Does it really just put 30 in? Or behind this single line of code, does there happen behavior such as allocating new memory, moving old data, releasing old space, and even interacting with the CPU's cache system? Today, let's take a look. One of the most commonly used data structures in C++, vector, how does it actually work? Vector is not an ordinary array. Many beginners think that vector is just an array that can automatically expand. That understanding is not exactly wrong, but there are still differences between vector and an array. When an ordinary array is created, its size is already fixed, and it will allocate a contiguous block of memory. But for vector, it does not know in advance how much data will need to be stored later. Maybe 10 today, and tomorrow it becomes 10,000. So vector needs to manage memory dynamically. Inside a vector object, it probably contains several important pieces of information, among which size, indicating how many elements are currently in it, and capacity, indicating how much space has been allocated so far. From this, we can also see that size and capacity are not the same thing. As shown in the figure, there are currently 5 elements in the vector, so size equals 5, but it has allocated 9 slots in advance, so capacity is 9. After storing 5 elements, there are still 4 slots unused. This is the key to vector's efficiency. At the very beginning, when you define a vector, there is nothing inside. Then in the code, you call the pushback method. At this time, vector will start to allocate memory. At the start, capacity equals 1. After push_back one element, the space is no longer enough, so it allocates larger memory and copies the old data over. But after continuing to push_back one more element, the memory may become like this. We will find that vector does not allocate memory every time an element is added. If it allocated memory every time, the performance would be very poor. So vector adopts a strategy, reserve extra space in advance. This capacity usually grows by a multiple. In this way, although occasionally data needs to be relocated, on average, the cost of each added element is reduced. This is what is called amortized constant time. But space will eventually run out. After executing one pushback, vector finds that it can no longer simply place the element in. So it has to allocate a larger block of memory again. First, allocate new space. This space is allocated in another block of memory. It is not expanded in place because the space right after it might already be occupied by others. Then move the old data over. In C++11 and later, move semantics are introduced. Vector will try to move the old objects to the new home, which is equivalent to directly pasting the door number of the old house onto the new house, saving the effort of copying furniture. Finally, release the old memory. So it looks like just executing one pushback statement. But in fact, it may execute a series of memory operations. After seeing this, think about one more question. Why is vector faster than linked lists? A very interesting point is that many people or courses tell you linked list insertion is fast. For example, here is a linked list containing 4 nodes. Each node stores data and the position of the next node. Theoretically, insertion only needs to change pointers, and it should be fast. But in the real world, vector is often faster than linked lists. This is a point contrary to intuition. The reason is also simple. Modern CPUs love contiguous memory. The data of vector is packed together. The CPU can load an entire chunk of data into the cache at once, which is cache locality. But linked list data may be scattered in different locations in memory. The CPU accesses one place for a while, then jumps to other locations, causing a large number of cache misses, and the CPU does not like waiting for memory. So although linked lists have an advantage in algorithmic complexity, in real hardware environments, vector is often faster. Unless you are inserting or deleting wildly at the front or in the middle, vector is often the better choice. At the same time, if you can know in advance roughly how much space the vector needs, you can use the reserve method to allocate space for the vector in advance. Then, when adding data later, there will be no frequent reallocation issues. In performance-sensitive programs, this little trick can be very important. So, on the surface, vector is just a dynamic array. But internally, it actually connects many underlying computer concepts. Understanding vector is not only about learning C++. It is also about understanding how software code actually runs on computer hardware.